Thank you, Nick, for the introduction, and a warm welcome to everyone. But before I begin, I would like to thank the organizers for giving me the opportunity to present at the DDL conference. Today I'm going to report about the impact of layer height on the quality of DPI prototypes prepared by mass stereolithography 3D printing. I think all of us can imagine that DPI device development, and especially the manufacture of suitable prototypes, can be challenging, so we're interested to see if MSLA 3D printing could be used in this context to make everyone's life a little easier. So what did we actually do in this study? First of all, we obtained a three-dimensional representation of a commercially available DPI by using CT imaging, and from that we generated a 3D printable model of it. The model was then 3D printed on a Prusa SL1 3D printer, using different settings for layer height, being 25, 50, and 100 micrometers respectively. While other parameters and the resin used were applied as recommended by the manufacturer. Then we compared the printed models by determining the intrinsic resistance and conducting comparative aerosol analysis of a model formulation. We also obtained CT scans of the printouts in order to evaluate their accuracy. Before we go into the data, I would like to just briefly touch on why we think MSLA 3D printing is an interesting option for rapid prototyping DPI devices, by highlighting that it is a very versatile method, which has very few restrictions to what is printable. Also, we have shorter processing times when compared to, for example, fused deposition modeling, whilst achieving a higher resolution of the printouts. So how does it work? In MSLA 3D printing, a photopolymerized resin is cured using a UV display that shows the geometry of the respective layer, and multiple layers are stacked to form a three-dimensional object. The resin is held within a tank, the transparent bottom part, that's placed above the display and in order to facilitate the curing. After the respective layer is cured, the printing platform is raised and the next layer is being added to the print. This process is being repeated until the full printout is obtained. The printable model we used differed from the injection molded template with regard to several aspects. Firstly, we omitted the pins and buttons, and in order to prime the capsule, it was inserted into a template DPI, pierced, and then transferred to our printed model using tweezers. Contrary to the template, in our model, the top and bottom parts are held together by screws. Other differences include the modification of the mouthpiece, as well as adding a seal to ensure airtightness. Also, the overall appearance of the model was modified with focus on printability. So if we take a look at the appearance of the printouts, we see that the overall quality is good, and that the printouts are a fairly accurate representation of the model. So our understanding of the mesh is the most critical geometry in this device, and on this slide we see CT images of all printouts, as well as a representation of the model file used. We can see that our printouts showed more narrow apertures when compared to the model, and this was more pronounced when using a layer height of 25 micrometers. If we take a closer look at the highlighted cells and determine their relative surface areas, it becomes apparent that we see a decrease of about 50% at a layer height of 25 micrometers, whereas printing with layer heights of 50 and 100 micrometers yields more accurate representations, being 89 and 85% of the surface area of the model respectively. This deviation is also reflected in the intrinsic resistance of the printout that was increased in all cases when compared to the template. This was also more pronounced when printing at a layer height of 25 micrometers. The similarity in surface area of the model generated using the 50 and 100 micrometer layer height setting was also reflected in their intrinsic resistances, which were also found to be comparable. Before we go into the cascade impactor data, let's take a quick look at the test formulation used. We used an API-only formulation of rifampicin that was manufactured by consecutive recrystallization and spray drying from ethanol. And as you can see in the SEM image, this yielded plate-like particles. The formulation shows good aerosol performance when analyzed with the NGI, with little deposition in the device and capsule, moderate deposition in the induction port, low deposition in the pre-separator unit, and an FPF of about 45%. So if we compare all three printouts, we see that all of them show similar powder retention within the capsule. Also, the retention within the device was comparable for all printouts, with the exception of the one generated with the 25 micrometer layer height setting, where a slightly lower deposition was observed. Deposition in the induction port was similar to the template in the case of the printouts used made using layer heights of 25 and 50 micrometers, but an increase in deposition was observed when printing at a layer height of 100 micrometers. This translated into fine particle fractions that were comparable to ones obtained with the injection molded template when using layer heights of 25 and 50 micrometers, whereas it decreased when using the 100 micrometer setting. So what we can conclude is that these results indicate that MSLA 3D printing is a suitable method for rapid prototyping DPIs if appropriate process parameters are applied. We can also conclude that the quality of the printout depends on the print settings, and this is also reflected in the cascade impactor data. Nevertheless, more investigation regarding other parameters and formulations is needed. Before I end this presentation, I would like to acknowledge Professor Thomas Bartholomeus from the University of Bonn for sharing the CT device. And also I would like to express my gratitude for financial support by the German Federal Ministry of Economic Affairs and Energy and the Galenis Privatstiftung, which is based in Vienna. Thank you for your attention and your interest in this presentation, and I'm looking forward to answer some questions.
Thanks, Kai. That was interesting to see. Do you have any feel for why the larger step up in your layers caused a higher deposition in the pre-separator? Sorry, the induction port.
The induction port. I think it's a quite complex topic because when you alter the apertures of the mesh, you will have differences in the flow pattern. And I think this is kind of related to what we just have heard before. So we might have different deagglomeration behavior. The exit velocities in this experimental setup should have been identical, so I think it might be related to this. So we have less deagglomeration, so we have higher impaction because we have agglomerates impacting in the induction port.
Okay. And in terms of material types, do you think that would make a difference? Because obviously the material you used for printing is different to what is commercially used. Yeah.
I think with respect to 3D printing or MSLA 3D printing, similar studies would have to be conducted for each material used, because also different resins differ in terms of their hardness and so on, which might also play a role, as we might have particle wall interactions and collisions and so on. So I think, yes, this is relevant. Also, the viscosity of the resin is important, because I think the differences we see in the accuracy of the different layer heights are also related to the viscosity of the resin.
All right. Thank you, Kai. I think this is interesting, and it starts to open a door for way forwards and different way forwards to do rapid prototyping. So thank you for sharing with us today.
Yeah, thanks as well.